In this video, we will look at 5 examples and examine whether the curly arrow mechanism shown is correct. You will learn how to correctly draw a reaction mechanism using curly arrows and also to spot when and where it went wrong. But before we begin, make sure you have a basic understanding of covalent bond formation, especially the octet rule, valency, and electronegativity. Also, know the rules for drawing curly arrows. There are 5 basic rules and I will place the link to a detailed article in the description. But for now, I will summarize those rules for you before we begin with the examples. The first and second rule are on arrow placement. The arrow base must be on an electron-rich site and the arrowhead must point to an electron-deficient site. Next, the arrows must move in one direction without converging or diverging. Fourth, the mechanisms that show the bond formation or breakage must respect an atom's valency. And finally, the preservation of the charges. The charge on the left side of the reaction arrow must be the same as on the right side of the reaction arrow. With the examples, you will learn more. So let's start. Example 1. From left to right, you can see that the arrow base is at the electron-rich oxygen atom and the arrowhead on the electron-deficient carbon. So the first rule of arrow placement is correct. The arrows move in one direction and do not converge or diverge following rule 3. And you can see that the CBr bond breaks to preserve the carbon's tetravalency, liberating bromide. So the commandment to preserve an atom's valency is also obeyed. And finally, conservation of charge rule. The negative charge of the oxide ion on the left is preserved with the bromide ion formation on the right. So the CBr bond, which is polar with electron density concentrated near the electronegative bromine, breaks in such a way that the charge resides on the bromine atom post the cleavage. So all 5 rules are followed and the mechanism shown here is correct. Let's go to the next example. The arrow base is on an electron-rich bond, but the arrowhead points not to an electron-deficient site, but an electron-rich site. Though the bond breakage will preserve the tetravalency of the carbon atom, however, such a bond breakage will still create 2 extremely unfavorable situations. The electronegative bromine atom, which should receive the bond's electron density and acquire a negative charge, instead develops a positive charge. And second, oxygen, a second row element that must have an octet of 8 electrons, would now contain 10 electrons. So the curly arrow mechanism shown here is incorrect. Moving on to example 3, from left to right in the first step, you can see how the electron-rich oxygen atom of water accepts a proton from the methyl oxonium ion, which in step 2 undergoes bond breakage, forming products methanol and hydronium ion. As you can see how the positive charge on the left in oxonium ion is conserved on the right in hydronium ion. Let's evaluate a little more. Due to the bond breakage in step 2, oxygen, a second row element, has preserved its octet configuration, divalency, and attained a neutral charge. A positive charge on an electronegative oxygen atom is not preferable. Therefore, the mechanism shown here using curly arrow is correct, following all the 5 rules. Moving on to example 4, definitely an incorrect way to represent curly arrow. The arrowhead is on an electron-rich site. Also, such a bond breakage would lead to a positive charge on the electronegative oxygen atom of the methyl oxonium and leave it with only 6 valence electrons instead of an octet. Therefore, it is highly unfavorable. Finally, in example 5, the flow of the arrow is in one direction, so that's correct. Let's read the reaction from right to left. The electron-rich hydroxide ion, by proton abstraction, forms a neutral water molecule. Bond breakage forms a carboxylate ion with a negative charge on the electronegative oxygen atom, which can be further stabilized by resonance, distributing the negative electron density over 3 atoms OCO. The negative charge on the left in the hydroxide ion is conserved with the carboxylate on the right. The arrowhead and base are all placed accurately, so the given mechanism is correct. If you have followed the video and would like to test yourself, take the quiz on CurlyArrows.com. The link to which I will place below. You can also visit CurlyArrows.com and sign up for the Organic Chemistry Fundamentals course, where I teach you all the basics required to excel in organic chemistry. In addition, we have books and study guides. For more such content, subscribe.